Hello and welcome to the review of Chapter 8, which will cover the binomial and geometric distributions. Starting with 8.1, which is the binomial distribution, if you recall, the binomial distribution is the discrete probability distribution of the number of successes in a sequence of n independent events. So, it must cover 4 criteria to be considered a binomial distribution. Each observation must fall into one of 2 categories, success or failure. It can't be both. There must be a fixed number of n observations, and these n observations must be independent. The probability of success, p, must be the same for each observation. Now, if you recall, there are 2 different types of binomial distributions. There's count and proportion. We're going to do a brief review on count. So when doing a sampling distribution of count, you must choose an SRS of size n from a population with the proportion p of success. Now, when the population is much larger than the sample, the count x of successes in the sample has approximately the binomial distribution with parameters n and p. When the population is big enough, you can assume normality. Now, when calculating the mean of count x, it's simply going to be n times p, or the number times our probability. The standard deviation, all under the square root, is just going to be np 1 minus p. If you recall, proportion, the mean of proportion is simply p, and the standard deviation of proportion is all under the square root, p multiplied by 1 minus p all over n. Now, when doing a binomial distribution, you're going to use normal CDF and normal PDF. Normal PDF will give you the exact number you're looking for. So if I wanted to plug in 3 in normal PDF, it would only give me the binomial distribution for the number 3. However, if I wanted to do normal CDF and I plugged in 3, it would give me the area. So essentially it would be 3, 2, 1, all the numbers below 3. Again, you can assume normality when n is large. You can also make a histogram of binomial distributions by entering data into L1, and for L2, entering binomial PDF and inserting your information. The calculator will compute it for you. You can do a cumulative distribution histogram, which is the same thing, except instead of PDF, you'll do CDF. Now, if you look at the top corner, you will see a somewhat complex formula that we're going to break down. In our notes, we used k instead of r, so k is the number of successes. So it's n choose k times p raised to the k times 1 minus p, or q, raised to the n minus k. P is the probability of success. R, or k, is the number of successes. 1 minus p, or q, is the probability of failures, while n minus k, or n minus r, is the number of failures. So in breaking it down, it's going to be n choose k multiplied by the probability of success raised to the number of successes multiplied by the probability of failures raised to the number of failures. So it's not as complex as it looks. That's just what your calculator is doing when you plug in binomial distribution functions. Next, we're going to discuss geometric distributions. So a geometric distribution is a random variable that counts the number of trials needed to obtain the first success. So, for example, say Kyrie Irving is taking a three-pointer and he's made 64% of his three-pointers this year. We're going to calculate at what trial it's going to take for him to make his first shot. So, again, it has 4 criteria that must be met. Each observation must fall into one of 2 categories, again, success or failure. All observations must be independent. The probability of success, p, must be the same for each observation, and this is where geometric is different than binomial. The variable of interest is the number of trials required to obtain first success. So now we're going to get into a couple of the formulas. So if x follows the geometric distribution, then the probability that the first success occurs on the, say, k trial is p multiplied by 1 minus p raised to k minus 1, or p times q raised to the k minus 1. It also has two functions, geometric PDF and geometric CDF, which is essentially the same thing as binomial, except it uses the geometric formula. So PDF is still for the exact number, while CDF is for the area. When looking for the mean of a geometric distribution, all you're going to do is you're just going to do 1 over p. For the standard deviation, you're going to do all under the square root 1 minus p divided by p squared. The probability that it takes more than k trials to see the first success is p, x is greater than k, equals 1 minus p raised to the k. So these are formulas that we'll need to memorize. They're not in the pink packet. And again, the formula you see in the top right is what your calculator is using when you use a geometric distribution. So like I said, the probability that it takes more than n trials to see the first success is going to be 1 minus p raised to the k, or the n in this case. Like binomial distributions, you can make histograms of geometric distributions. So you would enter the data in L1, then in L2, geometric PDF. So essentially everything for geometric and distribution or binomial distributions are the same except for the condition, and you're going to use the geometric function instead of the binomial function. So the tough part is distinguishing when you use binomial and when you use geometric. Geometric is used when you're trying to find how many trials it will take to get the first success. So that's how you should distinguish them. You can always do a cumulative distribution histogram by graphing L1 and doing geometric CDF instead of PDF. So that was just a brief overview on geometric and binomial distributions. I hope that was helpful.